So far we have discussed diatomic molecules. Now let us expand the scope of our discussion a little bit, and now we want to talk about not necessarily diatomic, not necessarily linear molecules. We want to talk about a little more bigger molecules, and while doing that we know that molecules have their own characteristic shape, right. So, this is something that we have studied Gillespie and Nyholm's approach of valence shell electron pair repulsion theory. There we know that we have an AB2 kind of molecule, then it is going to be linear. If it is AB3 where A is one atom, central atom, and B is another atom, you can say pendant atom, then we will get a trigonal planar molecule. AB4 tetrahedral, AB5 trigonal biplanar, trigonal bipyramid, sorry, AB6 octahedral, right. Of course, these are all regular solids, regular molecules, and these are all molecules in which you have a central atom, okay, holds very nicely for metal complexes, for example. And the reason why molecules have these shapes, please remember, because very often by mistake we put the cart before the horse. The reason why molecules have this shape is valence shell electron pair repulsion has to be minimized. So, if you have a situation in which you have two bonds, right, this is one bond, this is another bond. Then if they are like this and suppose there is no other lone pair or anything, there will be some repulsion. Then what will happen? They will try to open out, open out, open out. When they are at 180 degrees to each other, then this repulsion between what we can call bond pair of electrons is minimum. That is why AB2. So, 2 bonds means what? A central A atom, a B atom here and a B atom here. This AB2 is going to be a linear molecule. Okay. What happens if I have a trigonal planar molecule? Unfortunately, I do not have a third pen, so I will just use this. So, trigonal planar, again you have say 3 bonds, you put them at some angle, something like this, hold it like a pyramid, they are going to repel, 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 and finally if these bonds are all equal, if you remember we are talking about AB3 kind of molecules, which means all the bond pairs are equivalent, then the repulsion will be minimum when they are all in a plane and the angle between two is 120 degrees. So, generally when I go to class I do something which I have not been able to do today because, well, what I do in class is I take balloons, I blow up balloons and I tie them up, and I show that when you tie up 2 balloons, hold like this, you will always get a straight line, right, 2 balloons like this. Then if I tie 2 more balloons and wrap them together in front of your eyes, you get a tetrahedron. Yeah, balloons are balloons, there is no hybridization or nothing. So, what holds for balloons also holds for electron clouds, right, air in the balloon that wants to stay in a comfortable manner. Similarly, electron clouds want to stay in a comfortable manner. So, it is important to understand that VSEPR is essentially a steric effect. Okay. Lone pairs occupy more volume because they are not bound at one end. So, lone pair bond pair repulsion, lone pair repulsion is maximum, lone pair bond pair repulsion follows, bond pair repulsion is minimum. But whatever repulsion it is, you want to minimize it, and that is why the molecules take up whatever shape they take up. Okay. So, unfortunately right now we are in lockdown and I do not know where to buy balloons, and then I have to blow all of them up by myself. I do not have anybody to help. So, you do it yourself. Please blow up balloons, you might have seen it in parties and all. When they tie up balloons, they always tie in pairs and then they roll them together, and the shape you get is a tetrahedron. Why do you get a tetrahedron? Because a tetrahedron is the minimum bond pair repulsion geometry for an AB4 kind of molecule. Similarly, if you roll 2 more balloons there, you will get an octahedron, okay, and so on and so forth. You burst one of the balloons in octahedron, it will become trigonal bipyramid TBP in front of your eyes. Okay. Unfortunately, I cannot show that to you now, but I encourage you to please do the experiment yourself and see, it is a lot of fun. You can demonstrate it to even it is 5-year-old kid and they will be amazed and they will be amused and impressed, and well, it amuses me every time I do it. So, I hope it will amuse you as well, right. So, this is the crux of the matter. Molecules have certain shapes because of VSEPR. They want to minimize the lone pair, lone pair, lone pair, bond pair, bond pair, bond pair repulsions. The problem is this: if I want to build say a valence bond description of such a molecule, how do I do it? Because I have to use orbitals that are there in the atoms, right, atoms that constitute the molecules. How do I do it? Because for example, I want to talk about this AB3 kind of molecule, BF3 let us say. Boron has 2s orbital and 2p orbital. It does not have orbitals which have angles of 120 degrees between each other. So, what do I do? What I do is that I invoke hybridization, which means I mix orbitals and I make new orbitals, which gives us the suitable geometry required to minimize the lone pair, bond pair, bond pair, bond pair, etc. repulsions. So, please do not say that BF3 is trigonal planar because it uses sp2 hybridization. It is the other way around. BF3 uses sp2 hybrid orbitals of boron because it has to be trigonal planar, being an AB3 molecule, and that is determined by VSEPR, right. But perhaps I have also put the cart before the horse a little bit, because out of the blue I started talking about hybridization and hybrid orbitals without telling you what hybridization is and what am I talking about. Well, this is the more formal discussion. The handsome gentleman you see here is Linus Pauling, who has been one of the founding fathers of the field of chemical bonding especially, and Pauling, as you might know, got 2 Nobel Prizes, one in chemistry, one in peace. Very interesting life, he has done a lot of things. He wrote this book on chemical bonding, which for a long time was a textbook and now it has become a classic. You can read it very easily. I recommend that you read Pauling's book. And Pauling also proposed this vitamin C theory, by which he said that vitamin C is something that protects you from a lot of diseases. He also tried to work in the structure of biomolecules. A very illustrious career, extremely significant contribution to science. As long as human civilization exists in this present form, Pauling's name will not be forgotten. So, hybridization was one of the concepts that was introduced by Linus Pauling. So, what he said is that we need more effective bonding. More effective bonding means in this context we need to minimize these bond pair or whatever repulsions. To do that, since we do not have suitable orbitals, we have to produce suitable orbitals by taking linear combinations of atomic orbitals. Okay. So, this is a schematic energy diagram of 2s and 2p orbitals, remember, in a multi-electron atoms. I do not remember whether I said it in as many words, but what happens in multi-electron atoms is that because of shielding, 2s and 2p electrons now have different energies. You might remember that AsP, these are all atomic orbitals, and orbitals, as you better remember by now, me having said it so many times, are 1 electron wave functions. So, as long as it is a 1 electron system, 2s and 2p orbitals actually have the same energy. But in a multi-electron atom, many electron atom, the extent of shielding of 2s and 2p electron is not same. That is why 2p electrons have higher energy than 2s electron. So, what Pauling said is that let us mix a required number of orbitals, and we can mix them in different ways. We can think that we have applied a field which induces mixing, right. So, let us say we have mixed one orbital, let us say 2pz orbital. Generally what we do is we take z to be a unique axis. Let us say we have done mixing of 2s and 2p orbital, and we have made 2 orbitals. One is gamma 2s plus beta 2pz, sorry, alpha 2s plus beta 2pz, the other is gamma 2s plus delta 2pz, alright. So, now these are hybrid orbitals, and the picture that I am showing you here is the general picture, and sometimes people actually contest this picture because we are fixated upon thinking of equivalent hybrid orbitals. I will come to that. But please believe me for now that this is the most general picture in which you can apply some kind of a field, do something or require the molecule to undergo hybridization and make hybrid orbitals, right. These are coefficients alpha, beta, gamma, delta. Depending on the relative magnitudes of alpha, beta, gamma, delta, the energies of the two orbitals are going to be more or less or equal to each other. Okay. So, well, more about that shortly. See, these coefficients depend on field strength, and square of a coefficient is contribution of the atomic orbital in hybrid orbital. So, we have discussed linear combination already. We are going to discuss linear combination in the later stage of this course as well. So, what we know is that when we take linear combination and take mod square, the contribution comes from mod square of the coefficient. Okay. So, see in this orbital that I have drawn as lower in energy, mod alpha square or alpha square if alpha is real, that is going to give me the S contribution. Mod beta square or beta square if beta is real is going to give me the relative contribution of 2pz. Similarly here gamma square or mod gamma square will give me contribution of 2s, mod delta square or delta square will give me contribution of 2pz in this hybrid orbital. Now suppose mod alpha square is equal to mod gamma square, that means the orbitals are equivalent. That means they have the same contribution from s orbital, same contribution for p orbital. Okay. As you understand, energy of the orbital will depend on, since we are mixing now orbitals or wave functions that have little different energy from each other. If the contribution of 2s is more, then the energy of the hybrid orbital will be closer to that of 2s, that is lower in energy. If contribution of 2s is less, then the contribution of p is more, we say p character is more or p contribution is more, then that orbital will be closer in energy to p orbitals. So, that would be non-equivalent. But if what we have shown here, mod alpha square is equal to mod gamma square, mod beta square is equal to mod delta square, then you have equivalent hybrid orbitals. So, the hybrid orbitals that we have used many times right from class 11 or class 12, sp2, sp3, sp, these are all equivalent hybrid orbitals, but it is not necessary that they always have to be equivalent. So, in our discussion we will also talk about hybrid orbitals that are non-equivalent. We actually encountered them in say water. Okay. Orbitals used in bond pair, you need two such orbitals are equivalent of one kind, orbitals for lone pair are equivalent of another kind, the two types are not equivalent to each other. Okay. So, this is the most general picture, there is no need to think that hybrid orbitals must necessarily always be equivalent. If they are not equivalent, then you cannot use notations like your sp, sp2, sp3 and so on and so forth, that is all. Okay. Now, another important thing to remember is that hybrid orbitals are orthonormal to each other. Okay. We mix them in such a way, and we are actually going to do some calculations. So, this will become clearer when we do that. We mix them in such a way that they form an orthonormal set. So, take sp orbitals, the two sp orbitals are actually orthogonal to each other and they are normalized by themselves. That is how we calculate the coefficients in the first place. More about that when we come to it. Now, let us start talking about the first kind of hybrid equivalent hybridization that we want to discuss, and that is sp or hybridization. Okay, how do I decide whether I want sp or sp2 or sp3? Rule of thumb, number of hybrid orbitals is equal to number of participating atomic orbitals. And so, if you need two equivalent bonds like you do in acetylene, then I need one s orbital, s will always be there, I need only one p orbital to mix with s orbital. So, I use sp. If you want 3, what did I say? Did I say 1? If I have two bonds, two equivalent bonds like in acetylene part was correct, then we will do sp hybridization, because one s orbital, one p orbital makes to give you 2 sp hybrid orbitals, and how they look we will come to that. If I want to talk about BF3, then I need 3 equivalent hybrid orbitals for the 3 sigma bonds, right. So, then I need 3 orbitals, one is s, I need 2 of the p's. If I want to talk about methane, I need 4 orbitals for sigma bonds, 1 s and all the 3 p's, like that. Okay. Now, one thing that we should mention here, and this becomes most important because we are also going to talk about molecular orbital theory, and we already know about overlap integral from our discussion of your well, you did not take the name overlap integral then, discussion of many electron atoms. Please do not forget that s and p orbitals are of the same atom. So, overlap integral and all those things do not even arise. Okay, now let us go ahead. So, what we need is 2 equivalent hybrid orbitals of same energy and shape. Directions of course have to be at 180 degrees to each other, because we want to handle AB2 kind of systems. Okay. What do I do? This is what I need. I have an s orbital and I have a p orbital. What I am drawing here is your constant probability surfaces, not really orbitals. So, when we hybridize, I want to hybridize in such a way that I will get one orbital pointing this way, the other orbital pointing that way. So, I want a major lobe on one side, I want a minor lobe on the other side, and this black dot is a nucleus. Please note that the nucleus is within the minor lobe. This is another mistake that we sometimes make. We place the nucleus at the node, it is at the minor lobe, and I will convince you that the nucleus is in the minor lobe. Okay. So, it is very simple. I have only 2 orbitals here, s and p, and when I combine, essentially I need linear combination. So, when I have 2 functions, I can take 2 kinds of combinations, one with minus, one with plus, and then I want to normalize it, right. I said earlier that the hybrid orbitals have to form an orthonormal set. So, I take psi s plus psi s minus psi p, 1 by root 2 is normalization constant. Please check for yourself that psi 2 is normalized, psi 1 is normalized, not very difficult to see, because after all psi s and psi p by themselves are normalized. So, what is your integral psi 2 square, and should I write x? No, okay, I will write psi 2 square d tau, okay, but I will write it in a little shorthand notation. That will be equal to integral psi s square d tau plus integral psi p square d tau plus integral, I am not even writing the constants, alright. Oh no, I think I should. So, 1 by 2, no, this is 1 by 2, and this is going to be psi s psi p d tau, this is a 1 by 2 here, and 2. I hope you understood what I did. This is a plus b, right. So, what is a plus b whole square? That is a square plus 2ab plus b square, right. So, this is a square, this is 2ab, this is b square. But now we are talking about not any a and b, we are talking about orbitals. So, now see this integral here, what is this equal to? Integral psi s square, that is equal to 1, because psi s by itself is normalized. So, this thing becomes half. Second one again psi p is normalized, this thing becomes half, and here psi s and psi p remember are orthogonal to each other. So, this integral will be equal to 0, and this is what I said, do not get confused with overlap integral. We will get something like this later on when we talk about MO. Okay. Well, even in VBT we have discussed a little bit. So, we will do not think this is overlap integral. Overlap integral arises only when there are 2 nuclei, here there is only 1 nucleus. So, this is 0, this is 1, this is 1, this is half, this is half. So, half plus half is equal to 1. So, we have proven that psi 2 is normalized. Similarly, you can show that psi 1 is normalized as well. And what happens if I try to work out integral psi 1 psi 2 d tau? Psi s plus psi p, this is psi s minus psi p, and we have 1 by root 2 1 by root 2, that will be 1 by 2 integral psi s square d tau minus, I can take this outside the bracket, integral psi p square d tau. So, now we know this is 1, this is 1, 1 minus 1 is 0. So, we have proved that psi 1 and psi 2 actually are orthogonal to each other. Linear geometry with hybridized atom at the center. This is what we achieve when we use sp hybridization. But we have unfinished business. I told you that the nucleus actually resides in the minor lobe, which means that the way I have drawn it here, the minor lobes are actually overlapping with each other. I should actually prove it before we close this discussion. So, now see contribution from S, what is the contribution from S? Half. Contribution of P is also half. Okay. So, it is an equal mix, contribution is 0.5, 0.5, 50% S character, 50% P character. How did I get half? 1 by root 2 square, remember coefficient square. Okay. Now, let us think about the contours for the moment. This is the contour of sp hybrid orbital and I show you how we get it. This is where the nucleus is. As I said, the nucleus is actually engulfed by the minor lobe. Somehow this does not work on my computer, but if you go to this link, I have not checked it in a while, I hope it is still there. You can see very nicely how a 2s and a 2p orbital morph into giving you this sp hybrid orbital, and the reason why you get a node here and the reason why you get this nucleus engulfed by the minor lobe is that you are working with 2s orbital and 2s orbital itself has a node, right. So, let us see if you understand that a little better from here. Now, we go back to very early part, not very early part, sometime I do not remember, module 15, 16, where we had shown you the plots of orbitals against R. As I said, these are made by Professor Shashidhar about 21 years ago. So, this is the plot of your 2s orbital, right. 2s orbital has a radial node, goes through 0, changes sign and remains negative and becomes 0 asymptotically. So, this is a radial node and I had shown you the 3D picture. Actually, I have shown you a prettier 3D picture than what you show, this black and white picture that I show you here, and this is what it looks like. And you also know that this is what the plot of this 2pz orbital would be, 3D plot, psi on one axis, x and z on the other two axes, right. We have a hill, we have a trough, we have a valley. Now, let us do something. Let us take a section, let us take a razor blade and cut it from the top. Let us take a section of this 2s orbital, let us also take a section of this 2pz orbital. Okay. You understand what a section is, I am sure. You take a what should I say, take a watermelon and cut it. If you cut it this way, you see a cross section that is an oval, you cut it this way, you see a cross section that is about roughly a circle. Similarly, we are going to take a cross section and this is what we see. This here is your 2s, right, peak at the center, falls off, goes through the node, becomes negative, then goes through a minimum and becomes 0 asymptotically. Same thing on the other side. What about 2pz? Plus lobe here, then at the nucleus we have a node. That is a very important difference between 2s and 2p. 2s has maximum at the nucleus, 2p has maximum 0 node at the nucleus and there it changes sign. Now, do not forget the question we are trying to answer. We are trying to answer the question, why are we saying that the nucleus is engulfed by the minor lobe. So, now look at the periphery of the nucleus and let me acknowledge Professor Sandeep Kar, my colleague, who actually drew this picture and showed us that this is a good way to explain this. This picture I have not seen it in any textbook. Alright. So, now see near the nucleus, what is the value of 2pz? Close to nucleus it is 0. What is the value of 2s near the nucleus? It is very high. So, I hope you will agree with me that in the immediate vicinity of the nucleus, it is the value of the 2s orbital that is going to predominate. As you go further away, 2pz can take over. So, in the immediate vicinity, the value of 2s orbital is going to predominate. What happens if you go far away from nucleus on this side or that side? If you go to this side, you see 2pz is plus and 2s is negative, they cancel each other, you have destructive interference. So, you eventually reach 0. If you go to this side, then both are negative. So, there is constructive interference. So, your minor lobe is here, and I hope I have been able to convince you that all around the nucleus it is going to be plus sign, which according to this is the sign of 2s orbital near the nucleus, and that is the sign of the minor lobe. Usually minor lobe is showing with minus, but do not forget that that is just convention. We replace psi by minus psi, nothing changes, okay. Psi square mod psi square remains the same. So, this is what gives you this kind of major lobe, minor lobe, and the nucleus is within the minor lobe. I hope you have been convinced that this is how it happens. Alright. So, how does bonding take place? You have two sp orbitals overlapping like this, and the remaining p orbitals are available for pi bonding. That is why in acetylene you have one sigma orbital, then one pi orbital like this, one pi orbital like this. Say pz is used for sigma, is for hybridization, which is used for sigma bonding, px and py, or I should show like this, px and py are used for pi bonding, right. That is what we have discussed about linear geometry. Next, in the next class we will talk about trigonal geometry and sp2 hybrid orbitals.